Did you know that the voltage of the electricity in your home undergoes rapid changes? This is because the electric current alternates its direction continuously, creating what we call alternating current. If you were to graph the voltage over time, it would resemble a wave-like pattern, similar to a sine graph in trigonometry. Hence, we refer to this waveform as a sinusoidal wave. If the voltage is continually fluctuating, you might wonder why we use standardized values like 120 volt in Canada and the USA or 230 volt in places like England or India. What do these numbers signify when the voltage is in a constant state of change? You might assume that the voltage number represents either the highest peak or the average it reaches. However, that's not exactly the case. Enter RMS, root mean square, a fascinating concept used to measure voltage and current in AC electricity. Observing this basic circuit, there is a light bulb with resistance R. Once a direct current power source is connected, the bulb illuminates. To determine the current flowing through the circuit, we apply Ohm's law. Current equal to voltage divided by resistance. By rearranging this equation, we can compute the voltage is equal to current times resistance. Let's assign numbers to these two equations for reference. If we create a graph depicting both the voltage and current for the bulb, it will result in a straight line. You see, with direct current, both parameters remain constant throughout. Therefore, to determine the power consumption of the bulb, we simply multiply the voltage by the current. Simple, right? This represents our third equation. We can take the third equation and the first one to derive a new equation. Power equals the voltage squared divided by the resistance. Similarly, using the third equation with the second one allows us to derive another new equation. Power is equal to the current squared times the resistance. Keep these in mind. These two equations will be utilized later. Now, imagine a circuit using alternating current. Typically, we determine power by multiplying the voltage and current. But here's the twist. Both the current and voltage change in wavy patterns over time. So, how do we find the power now? We can multiply the voltage and current at every moment, creating a graph of the power. This power graph also oscillates in waves. Keep in mind, even if the voltage or current goes negative, the power is always positive. Examine these graphs. Voltage, current, and power all undergo continuous changes in AC systems. However, for calculations, we require some fixed values. How do we achieve that? Here's a simple trick. If we calculate the average power over one full cycle, it's consistently half of the peak power. What's the peak power? It's the highest value of voltage multiplied by the highest value of current. In essence, the average power in an AC system is always half of the peak power. Furthermore, the peak power is equal to the product of the peak voltage and the peak current. This relationship is crucial for understanding and calculating power in alternating current circuits. Returning to the circuit, we understand, according to Ohm's law, that despite the varying voltage and current, the ratio between voltage and current is consistently equal to the resistance of the light bulb. Let's rearrange the formula to express current as the subject. now armed with three equations. Let's endeavor to simplify them. Firstly, employing equations 2 and 3, we can articulate the peak power in terms of peak voltage and resistance. This represents our fourth equation. Subsequently, utilizing equations 1 and 4, we can formulate the expression for average power using voltage and resistance. The average power of an AC power circuit is equivalent to the squared peak voltage divided by twice the resistance. Let's revisit equation 3, rearrange it, and express the peak voltage in terms of peak current and resistance. Utilizing equations 2 and 3, we can then articulate the peak power using peak current and resistance, establishing our fifth equation. Now, employing equations 1 and 5, we can formulate the expression for average power using current and resistance. The average power of an AC power circuit is equal to the squared peak current multiplied by the resistance, divided by 2. Indeed, these two equations play a crucial role in understanding RMS. I hope the derivation process was clear. As you observed, arriving at these equations for AC circuits involved a more intricate path compared to DC circuits. Now, let's compare all the equations we've derived up to this point. These are the methods to calculate power in AC and DC circuits. In AC circuits, we use peak voltage and current. But here's the catch. We can't simply plug these peak values into the same formulas we used for DC circuits. We have to derive separate equations for AC, as demonstrated here. This requires additional effort. So, ingenious engineers attempted to define effective voltage and current values to represent AC systems. These values allow us to portray AC systems in a manner that aligns with the same equations used for DC circuits. We're employing a simple trick here. Assuming the resistance in both circuits is the same, we consider the power produced by both circuits to be equal. By utilizing equations 1 and 3, we can determine the DC circuit's equivalent voltage value for the AC circuit. Similarly, by using equations 2 and 4, we can ascertain the DC circuit's equivalent current value for the AC circuit. Using this DC circuit analogy makes calculations in AC systems more straightforward. These values derived are commonly known as root mean square values for AC systems. Almost always, RMS values are employed to express the voltage and current in AC systems. If your household voltage is 120 volts, this represents the RMS value of your domestic AC supply. Using our equation, you can determine the peak voltage of this supply, which amounts to approximately 169.7 volts. Alternatively, if your domestic voltage is 230 volts RMS, the corresponding peak voltage can be calculated using the same equation, resulting in an approximate value of 325.3 volts. That's all for today. If you think my contents are valuable to the world, you are welcome to join my Patreon community. Like and subscribe to Professor Mad for more interesting videos.